Hello, pre-calculus students. We're going to talk about section 721 and 722. So we're going to talk about average rate of change. And we're going to start talking about average rate of change as it relates to data. And then we're going to talk about it as it relates to functions. And I'm just having this like slight moment of panic about like that I'm not sharing my screen correctly. And that's why I keep toggling back and forth, because at first I did not hit record. And so I really hope that my screen is sharing right now. I guess we're going to find out. Okay, so 68, this is from 721. So as the shuttle mission STS-82 lifted off from the NASA launching pad at Cape Canaveral, Mission Control in Houston was receiving the following data about the altitude of the rocket in feet. So it says calculate the rocket's average velocity for the given time intervals below. Begin each calculation with the change in A over the change in T. So this little triangle here, that's delta. Delta A over delta T. Delta means change. So the change in the altitude divided by the change in the time. It says show your work for each calculation and be sure to include units in each of your calculations. So for part A, we want the change from T equals 3, so that's here, to time 21. Now, when you're doing this, you really want to make sure that you are using kind of this notation and really showing all your steps. So I know a lot of you are thinking, oh, I just need to subtract these and I need to subtract these and divide and be done. But I really want you to show what your work is here. So I want the change in altitude over the change in time. So I don't really want to write out the words change in altitude over change in time every time. So the change in altitude, I'm going to use delta A over delta T. So all of these are going to start with delta A over delta T. And to find the change in the altitude, I'm going to subtract. So 4,533 minus 70 over the change in time. So 21 minus 3. And so I'll figure out each of these differences. And then when I divide, I get 247.944. And it says make sure that you include units, so feet per second. Okay, so then for the next one, I want the change from T equals 3 to T equals 18. So here's T equals 3, here's T equals 18. You can see all of them are starting with T equals 3 and then going to times closer and closer to that 3. So I don't need to write out the words change in altitude over change in time every time, but I would like to see this delta A over delta T. And I would also like to see that you're doing the subtraction. So 3,200 minus 70 over 18 minus 3, and then subtract, and divide, and you get 208.667 feet per second. So again, you might be saying, oh, why do I have to write all this out? But we want to notice some patterns in like the structure of how we're doing this, because this is going to come into play as we start to generalize things later on in the section. Okay, so for C, I want from 3 to 15. I'm not going to do every single one of these, but we'll do this next one. So I would write the change in A over the change in T equals, again, I would subtract. So I would do 2,131 minus 70 over 15 minus 3, subtract, divide, and I get 171.75 feet per second. So you should do the remaining D through E. I'm going to just write up what the answers should be so that you can check as you go, but they should be set up like this. And then making sure that you are including units as you go. All right, so we'll look at another one. Okay, so for this one, same idea where we're looking at data, but now they're asking us some different things. So we have, what is the average rate of change of the altitude with respect to time? So again, altitude related to time. This one is what is the average rate of change of the pressure with respect to time. And then, well, then there are some kind of follow-up questions from there. So if I want the average rate of change of the altitude, so the altitude is in this column here with respect to time, from time is 360 to time is 650. So this is what I'm looking at calculating right here. So for part A, it's the change in the altitude over the change in the time. So the change in my altitude is 4,900 minus 2,900, and change of time is from 650 to 360. And so when I subtract, and divide, I get 6.897 feet per second. Okay, now part B is asking for the change in the temperature. And I don't know why there's this little like glitch here with a little symbol there, but I don't know. So I want the change in the pressure. So now I'm using these values. So change in the pressure for time is 650. So I'm using like this along with from 27, time is 2750. So I'm using this. So when I go to do this calculation, so this is the change in the pressure over the change in the time. So I'm going from 500. So I would do 500 minus 850 over 2750 minus 650. Now notice here, like 850 to 500, it went down. So that's, I'm getting a negative number over a positive number. So I'm getting negative 0.167 in this, my units here. And then C says, why is the rate in part A positive, the rate in part B is negative? Okay, so here, as the altitude is increasing, the pressure in the air is actually decreasing. Okay, and then D is asking, how's the temperature changing with respect to the altitude from time equals 0 to time equals 3,600. So now in this case, I want to know how the temperature is changing related to the altitude. So I want the change in the temperature over the change in the altitude. And it's when time is 0. So I want temperature and altitude, and then to the 3,600. Okay, so here I would have the negative 17.9 degrees Celsius minus 17.8 over the altitude here. So 24,900 minus ground level, which would be 0. And so I get a very, very, very small change in temperature per foot. Okay, so the idea here is we're using data to be able to describe these average rates of change. So when we find average rate of change in general, average rate, let's say rate of change, which will sometimes shorten, is equal to the change in Y over the change in X, which is really just our slope. Okay, so moving on to 722. 722 is the same idea where it's asking you, in this case, average velocity, which is still the average rate of change, but they give you a function, they don't give you data. So it says a car travels d of t, so distance, after a certain time, and the rule is 10t squared in for the first t seconds after it starts moving. Calculate the average velocity. So average velocity would be, what is it, feet per second. That would be our average velocity of the car by evaluating the change in the distance over the change in the time on the following intervals. So when we go to do the change in the distance over the change in the time, well, the thing is, I know, like, I'm going from 3 to 4, but I don't know what the corresponding distances are. And here's the graph would be a parabola, right, opening up. And so what I want to know is, and this is really little right here, 1, 2, 3, 3 is here. I want to know the change from when t is 3 to t is 4, which is up here. So I know it's 3 comma something and it's 4 comma something, but I don't know the y values like I did before. So I'm going to have to get my y values by using this rule. So I need to figure out, so here t is equal to 3. I need to know what d of 3 is. What is the y value when x is 3? So I would put 3 in here for t. So I do 10 times 3 squared, which is 10 times 9, which is 90 feet. Okay, I know when t is 4, that's my time, I need to know d of 4. I need to know the y value when that t value is 4. So 10 times 4 squared, which is 160 feet. So this is 390 and this is 160. So to get the average rate of change, now I'm going to do what I did before. So I'm going to find the change in my distances. So 160 minus 90 over 4 minus 3. So this is part A here, which would be 70 feet per second. Okay, so for each of these, before I can go to this formula here, I need to figure out what the corresponding y values. Now I already know for this one, d of 3, I already figured out that this is 90. I need to also figure out d of 3.1 to be able to find this average rate of change. So again, I'm going to put this 3.1 into this rule for t. So I'll have 10 times 3.1 squared. And then we'll figure out what that is. Let's do that really quick here. And then we can plug it into our rule. So 3.1 times 3.1, that's 9.61 times 10. So 96.1. So I would have to do 96.1, take away the 90, right? This y value minus this y value over 3.1 minus 3. And that comes out to be 61 feet per second. I would continue to do that for each of them. For each of these, I would find the corresponding y value, right? I already know this one's 90. I would find the corresponding y value and then do the change in y over the change in x, the change in the distances over the change in time. So I'm not going to do every single one of these. This should be 60.1 feet per second. Okay, you should do this. So if you missed this lesson, you should for sure do this on your own. If you're just reviewing, I guess that's kind of your call. Okay, but notice that in each of these cases, like there's always a 3 involved, and notice that these numbers here, these first ones are getting closer to 3 from the right, and then these other ones are getting, well, all of these are getting closer to 3 from the right, and these last ones are getting closer to 3 from the left. And then part G asks, well, overall at 3, what is the exact velocity of the car 3 seconds after it starts? So do you see how all of these numbers are getting closer and closer to 60? So we would say it seems like the exact velocity is 60 feet per second. And what's happening here is for this first one, so from 3 to 4, I'm finding the slope basically between these points. And so it's the slope of this line. Can't draw it very well. It's not coming out great. I want it to go through these points and it just totally is not. Okay, let's change to a highlighter here. My angle is funky when I do this. Okay, I basically want the slope of the line that goes through those 2 points. Okay, but then in the next one, so this is from 3 to 4, the next one is from 3, so here's 3 to 3.1, which is like right there. Now I'm finding the slope of the line through these points, and notice that they're not quite the same, right? The angle is, tilt is a little different. Then I'm finding the slope from 3 to 3.01, so like really, really close right after that. Notice that the distance between these is becoming smaller and smaller. And as that happens, this is morphing from, right now, we would say this is the slope of a secant line to the slope of what we're going to call a tangent line. And if you remember back from geometry, and I'm going to kind of skip 81 here for a second to talk about this because it's kind of an 82. If you remember back in geometry, if you had a line that went through a circle at 2 points, it was called a secant line. And if you had a line that just grazed the circle at 1 point, it was called the tangent line. Well, you can have secant and tangent lines to things other than circles. So right here is an example of a secant line, right? It's a line that goes through this curve at 2 different points. And so it says, how can an average rate of change be represented graphically given a function that is not a line? So if we look at this graph here, a line is drawn through 2 points, x1, f of x sub 1, and x sub 2 f of x sub 2. So sometimes people see that notation and they get kind of bogged down by the notation, like what does that mean? But remember, f of x is just code for y. This is like y sub 1, x1, y1, and this is like x sub 2, y sub 2. They're just using f of x and with a subscript of 1 and a subscript of 2. They're doing that to generalize things for when we have any formula. Okay, so it says a line passes through two distinct points on a curve is called a secant line, sort of like what we talked about here. Write an expression for the slope of the secant line that passes through these 2 points. Okay, so y2 minus y1, except for instead of using y2 minus y1, we're going to use f of x sub 2 minus f of x sub 1. So this is going back to what we were saying before about average rate of change, how this is the formula for average rate of change. Average rate of change. Okay, now I'm just using it with function notation. So I could write f of x sub 2 minus f of x sub 1 over, and this is subtraction here, over x sub 2 minus x sub 1. This is the slope of the secant line, or the slope of the secant line. And then it says, what is the average rate of change of f of x over the interval from x sub 1 to x sub 2? Okay, the slope of the secant line is the average rate of change. So when it says here, explain how a secant line can be used to graphically represent average rate of change of a nonlinear function, the average rate of change is the same thing as the slope of the secant line, which is, it just means slope. Okay, just they use a little fancier notation for function. It just means slope. And that's really what we were doing over here. Okay, as we get into sections 7.2.4 and 2.5, we're going to talk about what happens is that increment gets smaller and smaller and smaller. And how does that, it's going to lead us to what actually a derivative is. All right, so now 81, we're looking at this line, and first it says, what is the equation for the line? So lines are y equals mx plus b. Now, because I have a graph, I could just pick a couple of points. The scale is 1. I could say I'm going up 2, I'm going over 1. So my slope is 2. My y-intercept is here at -1. So there's my equation. And then it says, what is the average rate of change? And it gives you some different intervals. Okay, so I could do what I did on the last one and figure out what do I get when I put -1 in here for x? All right, so I could do 2 times -1 minus 1, that's -3. And then I could put 1 in here and do 2 times 1, which is 2 minus 1 is 1. And then I could do like the change in y over the change in x. So I could do 1 minus -3 over 1 minus -1. So that would be 4 over 2, which is 2. Because what I'm doing here is from -1 to 1, I'm trying to find that slope between those points, like our slope of our secant line. Well, because the points are actually on the line perfectly, my rise is 4, my run is 2, it's just 2. My average rate of change is 2 because that's just the slope of the line. Okay, so here I could do the same thing where I plug 1 in here for x, right? And I already know that that gives me 1. And then I could put 5 in here for x, so 10 minus 1 is 9. And I could do 9 minus 1 over 5 minus 1 and get 8 over 4, which is just 2. Which again should make sense because from here to any other point on the line, the slope is always 2. So here in D, when it says, what is the average rate of change from x equals 2 to x equals a, where a is any number? Because it's a line, the average rate of change is the slope of the line, it's always 2. So what do I notice about the average rate of change of a linear function, or how is the average rate of change related to the equation of a linear function? The average rate of change is equal to the slope of the line, always. So if I said, hey, here's this equation for this line, what's the average rate of change from x equals 0 to x equals any number in the world? We would say it is 4, right? It is just the slope. All right, so then in 83, okay, so 83, if we take a look at that, let me drag over my ebook here really quickly. So 83 asks us to look at some graphs, to visualize some graphs, and to talk about what is the average rate of change going to be? Is it going to be positive or is it going to be negative? So let's look here at 80. 3. So they give you all these different equations and they want you to visualize, is the average rate of change going to be positive or negative? And they want you to do that not by just plugging these numbers in like we were just doing, but by visualizing the graph, by saying to yourself, okay, that's a parabola from 2 to 3. What's going to be happening from 2 to 3 when I look at a parabola? So that's what they want you to be thinking about. So here, I already have these from class. So here is our parabola, right? And we want to know from 2 to 3 what is happening. So I drew in my slope of my secant line. You see how we have an increasing line. And if you have an increasing line, that means there's a positive slope. If there's a positive slope, that means the average rate of change is positive. So what I would suggest is, if you weren't here, like to take the time right now to do this, to think about what does a log equation look like and what would be happening from 0.01 to 1. If I drew in a secant line, would it be positive? Would it be increasing? Would it be decreasing? If it's increasing, then that means your average rate of change is positive. If the slope of the secant line is negative, then it means it will be decreasing. So I'm going to just quickly kind of go through these, but you should try them on your own first before you just like look at this. Okay, so the next one is a log. So here's my log graph. Maybe, wait for it. Here's my log graph. Okay, here are my two values between which I'm trying to say what my average rate of change is. If I drew the secant line in, it's increasing. That means the average rate of change would be positive. So these answers are asking, is it positive or negative? Your answer should be either positive or negative, not increasing or decreasing. All right, we had done an activity in class. Okay, the next one is an upside down parabola. So part C is an upside down parabola. And the points were from 2 to 5. You see this line would be decreasing. So then that means that it would be a negative average rate of change. All right, the next one was exponential decay. So it was 0.5 to the x. So it's always decreasing. Because it's always decreasing, you always have a decreasing line for your tangent, or your secant rather. And so a negative average rate of change. You missed out on a good activity if you weren't in class. All right. For E, it's exponential growth. It's always increasing. So you have an increasing secant line. That means you have a positive average rate of change. And for the last one, it's just y equals x squared. And it would be, again, an increasing secant line, which means a positive average rate of change. Now, just because like here, it's positive, I picked these values, but let's say I had said from -2 to 0, like that would be a decreasing secant line, and it would be a negative average rate of change. So it depends not only on the function you're looking at, but it also depends on between what two values you're looking at. All right, that takes care of our introduction to average rate of change.